Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1866 publication by Alfred Clebsch and Paul Gordan, Theorie der Abelschen Funktionen, represents a monumental synthesis in 19th century mathematics, a work whose title modestly obscures its revolutionary, methodological core, while ostensibly a treatise on higher-order transcendental functions. Its enduring legacy lies in the systematic and powerful development of algebraic invariant theory as the primary engine of geometric discovery. This essay will undertake a direct evaluation of the work's internal claims, proceeding section by section to analyze the specific arguments, frameworks, and conceptual mechanisms presented by its authors. The focus will remain tightly on the text itself, examining how Clebsch and Gordan constructed and deployed their theory, assessing the coherence of their logic, and exploring the profound implications of their symbolic calculus for the unification of algebra and geometry. We will trace the work's intellectual trajectory from its foundational symbolic representations to its ambitious application, evaluating the claims made for this new and formidable mathematical language. Section 1. The symbolic method as a universal language for forms. The work's initial sections lay a foundation of startling ingenuity, proposing a new symbolic language for the study of algebraic forms. The central claim here is that any binary form, say a function f for variables x sub 1 and x sub 2 of degree n, can be completely represented by the nth power of a symbolic linear expression. This is written as the quantity alpha sub 1 times x sub 1 plus alpha sub 2 times x sub 2, all raised to the power of n. In their compact notation, this becomes alpha sub x raised to the power of n. The coefficients of the original form are then recovered by treating the powers of the symbols alpha sub 1 and alpha sub 2 as the actual coefficients. The profound claim is one of ontological equivalence. The form and its symbolic representation are interchangeable for the purposes of discovering its intrinsic properties. The evidence provided is procedural. Clebsch and Gordan demonstrate that this substitution works and allows for manipulation otherwise impossible. The evaluation of this claim reveals its deep conceptual power by detaching the coefficients from their fixed numerical values and giving them a symbolic, almost animate, existence. They transform the study of forms from a static analysis of polynomials into a dynamic calculus of interacting symbols. The argument is one of utility and creative potential, a hermeneutic key that unlocks a hidden world. The internal logic is compelling, as they show how a second form, xi, can be similarly represented as beta sub x to the power of m, allowing for the interaction between two distinct algebraic entities to be studied through the interplay of their respective symbols, alpha and beta. This foundational step claims that the entire universe of a form's properties is encoded within these symbolic potentials. Section 2. The translectant as the sole engine of covariant construction. Building upon the symbolic language, the authors introduce a single, powerful operation they call the Überschiebung, or transvectant. The work's claim in this section is that this one mechanism is sufficient for generating the entire hierarchy of invariants and covariants of a given system of forms. The kth transectant of two forms, f represented as alpha sub x to the power n and g represented as beta sub x to the power m, is defined symbolically. It is given by the determinant of alpha sub 1 and beta sub 2 minus alpha sub 2 and beta sub 1, all raised to the power k, multiplied by alpha sub x raised to the power of n minus k, and further multiplied by beta sub x to the power of m minus k. The assertion is that any polynomial in the coefficients and variables that exhibits the required invariance or covariance properties can be constructed through a sequence of these transectant operations. The methodology here is exemplary. They provide concrete examples, building up known covariants like the Hessian and the Jacobian from simpler forms using only this operation. The evaluation of this claim points to a profound desire for systematization. The transactant becomes the atom of their algebraic chemistry, the fundamental interaction from which all complex structures are built. The evidence is constructive. They build the world they describe. By demonstrating its generative capacity, they implicitly argue for its completeness. A certain intellectual aesthetic is at play, a paring down of complexity to a single elegant mechanism. The claim's strength lies in its operational success within the paper's confines. The transactant appears as a veritable philosopher's stone, capable of transmuting basic forms into treasures of geometric significance. Section 3. A projective correspondence doctrine. Here, the work makes its most central and philosophically resonant claim that a perfect correspondence exists between the algebraic facts of the symbolic calculus and the projective geometric properties of the curve or surface defined by the form. An invariant or covariant is interesting precisely because its structure or its vanishing signals a specific, coordinate-independent geometric event. The argument is advanced through a series of masterfully chosen examples. For a binary quartic form, they construct a specific invariant, which they demonstrate vanishes if and only if the 4 points on the projective line represented by roots of the form are in a harmonic configuration. The vanishing of the discriminant, a fundamental invariant, is shown to correspond to the geometric condition of 2 roots, and thus 2 points, coinciding. The methodology is one of translation. They establish a lexicon for moving between the 2 realms. The algebra of symbolic brackets, like the determinant of alpha and beta, becomes the geometry of relative positions. Evaluating this claim reveals the deep motivation of the entire enterprise. The symbolic method is a tool, but geometry is the truth it seeks to uncover. The evidence provided is overwhelmingly persuasive for its time, creating a compelling narrative where abstract calculations on one side yield tangible, visualizable properties on the other. This section argues for a preordained harmony between the world of pure symbols and the world of spatial configurations. The success of this argument established a paradigm for algebraic geometry that would hold for decades, positing that to understand a geometric object is to understand its complete system of invariants and covariants. Section 4. The implicit postulate of finiteness and complete systems throughout their analysis of specific forms, particularly the binary cubic, quartic, and quintic. Clebsch and Gordan operate on a powerful and generative, yet unproven, assumption. This is the claim that for any given binary form, there exists a finite set of fundamental invariants and covariants, the complete system, from which all other such entities can be generated through algebraic combination. While Paul Gordan would famously prove this finiteness theorem for binary forms 2 years later, whose of 1968, those of 1966 work proceeds with the full confidence of its truth. The claim is embedded in their methodology. Their goal in analyzing the quintic, for instance, is the enumeration of its 23 fundamental forms. The internal argument is one of exhaustion. They develop systematic, albeit heroically laborious, techniques for finding all irreducible forms up to a certain degree, and by structuring these results, they present a compelling case for the system's completeness. The evaluation of this section is fascinating. It shows a mathematical theory being built upon a foundational pillar that is, at the moment of construction, an article of faith. The intellectual fortitude required to undertake the immense calculations for the quintic, all guided by the belief in a finite, discoverable goal, is a testament to their conviction. The paper's claim is pragmatic. Our method allows for the construction of what appears to be a complete system, and this system is immensely useful. This implicit belief in finite generation is perhaps the work's most significant forward-looking claim, shaping the direction of invariant theory for the next generation and setting the stage for one of its most celebrated results. Section 5. The extension of symbolic methods to ternary forms. Having established their machinery in the relatively tractable domain of binary forms, which correspond geometrically to points on a line. The authors then claim the applicability of their symbolic methods to more complex cases. Specifically, they turned ternary forms, whose vanishing defines algebraic curves in the projective plane. The core assertion is that the symbolic language and the transectant operation, with appropriate modifications, retain their power and interpretive relevance in this higher dimensional setting. A ternary form is now represented symbolically as alpha sub x to the power of n, where x represents a vector of three variables, x sub 1, x sub 2, and x sub 3. The symbolic bracket, which in the binary case was a 2-byte word determinant, now becomes a 3x3 determinant of the symbols from three different forms. For example, the determinant of alpha, beta, and gamma. The authors claim this generalized determinant is the fundamental building block for invariants of ternary forms. Their method is to demonstrate the construction of well-known covariants, like the Hessian, which geometrically represents the inflection points of the curve. Using this new symbolic apparatus, the evaluation of this claim reveals both the strength and the emerging challenges of their system. The elegance of the binary case is somewhat diminished by the combinatorial explosion of complexity. Generating invariants requires combining three or more forms, and the calculations become significantly more involved. However, the conceptual claim holds the method provides a systematic, if arduous, path to understanding the projective properties of plane curves. They successfully show that the Hessian of a cubic curve is a covariant of degree 3, and its vanishing at a point on the curve signals that the point is an inflection point. This section substantiates their claim of scalability, proving that their framework is a genuine theory of algebraic forms, a tool applicable beyond its initial testing ground. Section 6. The geometrization of concomitants for plane curves. This section deepens the investigation of ternary forms by making explicit claims about the geometric meaning of a wider array of concomitants, a term embracing both invariants and covariants. The authors advance the argument that the entire structure of a plane algebraic curve, its singularities, its tangent structure, and its relationship to other curves, is encoded in its system of concomitants. They examine the ternary cubic, a plane elliptic curve in the general case, with extraordinary thoroughness. They construct its two fundamental invariants of degree 4 and degree 6, claiming that the geometric properties of the curve are functions of these two numbers. For instance, the condition for the cubic to degenerate into a set of lines is expressed as a specific algebraic relation between these two invariants. The methodology becomes a virtuosic display of the correspondence principle. They introduce covariants, like the Pippian and the Quippian, esoteric constructions of the symbolic calculus, and then provide their precise geometric interpretations in relation to the curve's properties. In evaluating this claim, one perceives the apotheosis of their project. The geometric object, the plane curve, is almost dissolved into its algebraic shadow, the system of concomitants. The argument asserts that to know this system is to know the curve in its entirety, in a way that transcends any particular coordinate system. The evidence is the beautiful and intricate web of connections they weave. While a modern geometer might use different tools, the fundamental claim that the intrinsic geometry is captured by such algebraic data remains a cornerstone of the field. This section validates the entire program by showing its profound descriptive power when applied to one of the most important objects in 19th century geometry. Section 7. The synthesis of invariant theory with abelian functions. The final and titular ambition of the work is to apply this powerful invariant theoretic machinery to the theory of abelian functions. The central claim here is that the moduli of algebraic curves, which are the essential parameters governing the associated abelian integrals, can be understood as rational functions of the absolute invariants of the underlying form. For the case of a plane cubic, corresponding to elliptic functions, they demonstrate that the absolute invariant formed as a specific ratio of the fundamental invariants of degree 4 and 6 to avoid homogeneity issues, is precisely the modulus that appears in the classical theory of elliptic functions. This is a unification of immense significance. The methodology is to connect two previously separate mathematical domains. They take the abstractly generated invariants from their symbolic calculus and show that these quantities are the same as the parameters emerging from the analytic theory of integration on curves. The evaluation of this claim marks the triumphant completion of their argument. The entire development of the symbolic method now appears as a grand prolegomena to this final synthesis. It provides a purely algebraic, and in principle constructive, path to the foundational parameters of a deep analytic theory. The work successfully argues the theory of algebraic invariants is the natural language for the problem of moduli, the problem of classifying curves up to projective equivalence. This claim fundamentally reoriented the study of higher-order functions, rooting it firmly in the soil of projective geometry and its corresponding algebraic counterpart. It demonstrated that the properties of functions defined on a curve were ultimately dictated by the invariant theoretic structure of the polynomial defining at curve. In conclusion, the 1866 Theorie der abelschen Funktionen stands as a landmark of deductive and constructive reasoning. Its primary claims, evaluated in sequence, reveal a meticulously constructed intellectual edifice. The work argued for the universality of its symbolic language, the generative power of the transectant operation, and the perfect correspondence between algebraic symbols and geometric reality. It proceeded with a confident belief in the finiteness of invariant systems, a conviction that propelled its ambitious computational and theoretical agenda. The authors successfully demonstrated the scalability of their methods from binary to ternary forms, culminating in a profound synthesis with the analytic theory of abelian functions. The internal logic of the paper is one of self-reinforcing demonstration. Each stage provides the tools and justification for the next, building from a simple symbolic substitution to a framework capable of classifying complex geometric and analytic structures, while subsequent developments in mathematics, particularly the abstract algebra of M. E. Noether, would provide a more powerful and elegant foundation for invariant theory. The work of Clebsch and Gordan remains a singular achievement. Its claims, assessed on their own terms, represent the apotheosis of the constructive, algorithmic spirit in 19th-century mathematics, a compelling and beautiful argument for the deep unity of algebraic form and geometric meaning.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.